Hasita. I'm making this video for the project demonstration. The project main goal is to solve the traveling salesman problem, which involves determining the shortest possible route that visits each city exactly once and returning to the starting city. The project focuses on the TCP. It implements two algorithms, brute force algorithm and approximation algorithm based on MST, minimum spanning tree. The brute force algorithm exhaustively analyzes every potential combination of cities to find the route with the lowest cost, while the MST based approximation approach builds a minimum spanning tree of the cities and then traverses the tree to find a path that is within the factor of 2 of the optimal solution. Um, so I will show the implementation part. So this is the Python code uh, which implements the traveling salesman problem with the using the two uh, algorithms, brute force and approximation one. The first function here is a TCP brute force, which takes the two arguments as input, which is n and distances, where n is the number of cities and distances is a 2D array that represents the distance between the cities. The function returns the shortest path and the cost of TCP using the brute force algorithm. The function works by generating all the possible permutations of the cities and computing the cost of each permutation. The permutation with the minimum cost is returned as the shortest path. So in the second function, as we can see, is a TSP approx MST is an approximation algorithm for solving the traveling salesman problem based on the minimum spanning tree. And the function here takes the input number of cities n and the distance, metric distance between the specifies uh, the distance between every pair of cities. The function starts by analyzing an empty set visited to keep the track of the cities that have been visited so far. An empty list MST underscore path to store the edges of the minimum spanning tree. A variable MST underscore cost is there to keep the track of the total cost of the minimum spanning tree, and a variable current underscore city to keep the track of the current city. The function then enters into the loop uh, that continues until all cities have been visited. In each iteration of the loop, the function finds the nearest unvisited city to the current city by looking at the distances between the current city and every unvisited city. It then adds the edge connecting the current city and the nearest unvisited city to the MST path list. Update the MST cost variable with the weight of the new edge and sets the nearest unvisited city as the current new city. The function also adds the new current city to the visited set. After all cities have been visited, the function adds the edge connecting the last visited city back to the starting city to complete the tour. The function then returns MST path and the MST cost variable as the approximate solution to the TCP. The code also includes an example usage section which demonstrate how to use the function to solve the TSP for a number of cities using the brute force algorithm and for a range of larger values of n using the approximation based on MST. The brute force algorithm is implemented in the TCP brute force function as I showed above, and is used to compare the results with the approximation algorithm. The time taken to solve the TSP for each value of n is also printed to demonstrate the difference in efficiency between the brute force and approximation algorithms. The output of the code shows here the output of the code shows the results of running both algorithms on randomly generated distances between randomly generated distance matrices for different values of n, which is the number of cities. And for the brute force algorithm, the output shows the distance matrix here, the shortest path, and the cost and the time taken. For the MST approximation algorithm, the output shows the same information for each value of n, which is n equal to 5, and it also shows for n equal to 1000. I think it will take some time to show the output. Yeah, as you can see here, uh, it shows the result for n equal to 1000, and the distance matrix and shortest path and the cost and time taken. And I will also show the graph. We can I've also added the graph part for the brute force and approximation MST. When we run this, we will get a graph for like this. I've also added in the report. I will show the report for the better view. So this is for the table, which includes theoretical complexity, empirical RT ratio, and these are the graphs which I've implemented there. So to compare the performance of the two algorithms, the project conducts an experiment using random distance matrix for different values of n. For small values of n, the brute force algorithm is used to find the optimal solution, while for the larger values of n, the MST based approximation algorithm is used. The experiment measures the time it takes to find the solution and the effectiveness of the solution. So the project also includes the tables to show the theoretical, sorry for that, it shows the tables to show the theoretical and empirical time complexity of both algorithms for different values of n. This table can be used to predict the expected running time for a given input size. Overall, the project provides a comprehensive solution to the TSP problem using both exact and approximation algorithms to find the optimal route for visiting a set of cities. Thank you.